All right, folks. Here's a video from week 25 Thursday, number 22, 23, and 24. Okay. So let's start with 22. 22. The reason why you guys might have a question is simply because there is a typo. This should say 0. Maybe that was the question that you guys had. So if you look at the graph, I'm just going to do it on Desmos real quick to save time. If you look right here, okay, we got the red graph. Okay, we got these 3. 1, 2, 3 pieces, which are showing right over here. Okay, they're showing right over here. So what we're essentially going to be doing, okay, let me just copy and paste this over here. Oh, wait for it to load. Okay, so we have this right over here. We have these 3 being these 3, and we are going to revolve it around. We're going to revolve this, okay, this around the blue line. Okay, it's going to create a solid. So we're going to use lower and upper bound of 0 and 4. Okay, of 0 and 4. So this should say 0. And we are going to do oh, sorry, I just brain farted for a little bit. We're going to do root x. Let me get my symbols over here. Okay. Root x minus 2. Okay. Let's go like that. What's the best way of describing this? We're going to go root x minus 2. Here, let me just visually show you guys like this. Okay, this is y equals 2. It's like that. Okay, that's for the red. All right. And this is going to be y equals 2. Negative 2 for the blue. Okay. So let's say, again, hypothetically speaking, we have a y coordinate here of, okay, a y coordinate up here of negative 1. Okay. You're going to have to subtract negative 2. Okay, let's actually call this right here negative 0.5. Okay, negative 0.5 right there. And this is negative 2. So so we would have to do in this hypothetical case, okay, negative 0.5 minus negative 2, okay, which would give us 1.5, okay, which would be the distance here, which would be the radius of this vertical cross section. Okay, this vertical cross section, this hypothetical case, the radius would be 1.5, and we get that officially from doing negative 0.5 minus negative 2. So whatever the y coordinate is up top over here, we subtract negative 2. So we are going to go like this, boom, minus negative 2, okay, and double negative becomes positive. Negative 2 plus 2 becomes a clean root x, okay. So this just becomes a clean root x right over here. Okay. Like that. Okay. And you just extract the pi outside the integral and you get to and then you can see what they got over here. It matches up with what they got. It just should say 0 right here from 0 to 4 because your upper lower bound is 0 and 4. Your lower upper bound is 0 and 4 right here. Okay. So that's number 22. Let's go on to number 23. 23, let me get the graph right over here. So boom, let's grab that. Let's paste it on the right hand side. Okay, so for 23, we got these two right here, okay? And we're going to revolve this around, okay? We're going to revolve this around the x equal to 1 line, okay? So we're going to revolve it around this, okay? And what exactly are we revolving? We're revolving this orange highlight, okay? So this would be a situation where we have our clear lower and upper bound vertically stacked, bottom and top. So it would make sense to integrate this with respect to y, which means if you want to apply the hack, is turn your head like a confused dog 90 degrees to the left. Okay, so our upper lower bound with respect to y would be -1, 1. Okay, and remember now we have to get everything in terms of y, which means we have to isolate x. When you isolate x here, okay, you get this, and then this ultimately. Okay, and you got to, and think about it like this. Let's say this, x coordinate, okay, is 1.75. Because this is x equals to 1, the distance between the two pink dots would be 0.75. So whatever the x coordinate is over here, you have to subtract 1, okay, to get you have to subtract 1 in order to get the difference between the two, which would make the radius of one cross section. Okay, so what we're going to be doing here, let me actually rewrite this here. Let me save that real quick. It's been known to freeze. And so what we're going to end up doing is subtracting a 1 over here. Okay, all right. Right over here, let's subtract a 1. Okay, so this ends up being -y squared plus 1. Okay, I mistakenly over here typed stuff in as if it was a washer. And so we end up getting that right there, and we just cut that out. Okay, and now what they did to get from here, to get from this step to this step, just extract the pi out of the integral, and we integrate from -1 to 1. Okay, again, in the hypothetical case, we pretend this is 1.75, and this is 1 because x equals to 1. The distance over here is going to be 0.75 because 1.75 minus 1 is 0.75 in this hypothetical case. But this is actually, so whatever the x coordinate is over here, which is -y squared plus 2 in general variable form, we subtract 1 from that. Okay, 2 minus 1 gives you this 1, and then we just extract the pi, and that leaves us here with a lower bound, upper bound of -1, 1. Okay, let's look at number 24. Okay, let me save this, copy, paste. Let's get this out the way. Okay, and let's look over here. Okay, boom, and let's move everything to the right to create space. Now, we basically have this pink that we want to rotate around, okay, the green line. All right, so we got that pink we want to rotate around the green line. So again, we have some clear upper lower bounds defined vertically, stacked vertically. So we're gonna use lower upper bounds that are vertical, which means we're going to integrate with respect to y. Okay, your upper lower bound is going to be -1, 1. Okay, and ultimately the way that we're going to use the washer. Okay, we're going to use the washer method, whereas we use the disk method, if my memory is correct, in the past two problems, 22 and 23. So the key thing to remember is that if you do blue, okay, blue minus, let's see if I can bring this back, okay, blue minus, I'm going to call this the white zone, okay, so blue minus white, this blue minus this white is going to give you the remaining pink, okay, and so the blue is going to be, let me be consistent with my colors here. Okay. All right. So let me actually change this to pink and change this over here and change this to blue right here. Okay. And do I want to keep that blue? Yeah. Okay, so again, pink minus the white will give you the remaining blue. Okay, so let's look right here. We're going to get x by itself, again, because we're integrating with respect to y. We want to get x by itself. So when you get x by itself, okay, when you get x by itself, this and this become this and this without the minus 2. Okay, now why do we minus 2? For the same reason I described in the previous problems. Okay, whatever the x coordinate is, okay, whatever the x coordinate is over here, you want to subtract 2 from it, okay, in order to get the distance between the grays. Okay, same thing over here. Whatever the x coordinate is over here, you want to subtract 2 from it to get the distance between these two grays. Okay, when it comes to the blue graph. So whether it's the blue line or the red, whether there's a blue function or the red function, you always have to subtract 2, which is the x value of the green line, to get the distance between the gray. Okay, because we're interested in that distance in order to get the radius. And I misspoke earlier. This pink, okay, I did the pink from up until the x-axis, the y-axis. It should really be this pink right here. Okay, it should really be that pink right there. So let me bring this to the front. Okay, it should really be this pink. So again, this pink minus this white, okay, it should equal to the blue. All right, that's what I should have said. So now, so that's why we subtract 2 from each case, okay, for the reasons I said a second ago. So 7 minus 2 gives you the 5, 5 minus 2 gives you this 3, okay. So, so now we're going to use the washer method. We're going to do pink, okay, we're going to revolve the pink, which is related to the red graph, around the green vertical line, and that is going to be pi r squared, r being the red graph, okay, the red function rather, okay, so that's this right here, that's this right here, okay, and then we're going to subtract, okay, we're going to subtract the volume of revolving the blue around the green, the blue function around the green vertical line. Okay, so let me use blue right here. Okay, whoops. Let me use blue. Okay, blue. I shouldn't use blue, that blue, because then you're going to think it's that blue right there. Let me use orange. Okay, this is the orange right here, which is, okay, which is that. All right, so pink. So pink minus the orange will give you this blue. So we're going to revolve the blue graph. We're going to revolve the solid created by the blue in between the blue graph and the green line, which would be the orange. Okay, so basically pink volume. Pink, if you treat the volume like the disk, if you treat the volume of revolving the pink around the green minus the orange around the green, okay, using the disk method for each, and you subtract the disk method for each from each other, which creates the washer method, okay, you end up getting this minus this. Okay, so pink volume minus orange volume revolved around the green basically gives you this right here. Okay, and so you just simplify from here, GCF the pi, extract the pi, and then remember, upper lower bound is going to be negative pi and pi, okay, or excuse me, negative 1 and 1, okay, boom, boom. All right, let me just get my colors the same, and you just put that in your calculator. Okay, folks, I hope that clears things up. Thanks for tuning in.